In this tutorial, I'll discuss the concept of HVAC loops, used to model HVAC fluid flow and return systems in DesignBuilder. I'll use a relatively simple hot water loop as a vehicle to highlight important aspects of the loop, but the finer details of the individual components are covered in later tutorials. During the tutorial, I'll discuss the HVAC loop concept, show you how to add a hot water loop, show you how to add zone components and connect the system, and finally I'll run a quick simulation and review the results. HVAC loops are used to model energy flows in a HVAC system, supplying air and hot and chilled water where relevant to provide heating, ventilation, air conditioning and domestic hot water. Here is a schematic representation of a simple hot water loop, which contains a demand subloop here at the bottom and a supply subloop here at the top. The demand subloop contains the zones and their HVAC components where energy is consumed. This creates a load on the system, which is met by the HVAC plant and controls here in the supply subloop. The schematic diagram created in DesignBuilder represents HVAC components connected together by pipes or ducts to form distribution systems. Here is the schematic of a variable air volume or VAV with zone reheat system. The conditioned fluids are supplied from the plant in the supply subloop via pipes and ducts to the demand subloop. That energy is consumed in the demand subloop to meet the zone HVAC or domestic hot water load. Then the fluid is returned back to the supply subloop for reconditioning or possibly exhaust in the case of an air loop. Note that the air and water loops can supply zone groups and other HVAC system components, shown here by the hot water loop, which supplies heating coils in both the zone terminal units and the air handling unit. At the HVAC system level, you can see the different types of loop available in DesignBuilder by clicking on the Add Loop icon. The main types of loop currently available are the air loop, which can provide ventilation, heating, cooling and humidity control depending on the system type. Water loops, which can provide hot and chilled water to plant and terminal units. Condenser loops between water-cooled chillers and cooling towers. Domestic hot water or DHW loops. And solar thermal loops. The different loop types are also shown here in the info panel in their respective groupings, where you can see that there are a number of different types of air and water loop. These will be covered in detail in a later tutorial. In this and all future detailed HVAC tutorials, the HVAC activity data is set to simple in model options unless otherwise stated. A single zone group has been created containing all the zones in the building. As I'm modelling a heating system, I'll reduce the zone heating design margin to 20% by changing it in one of the zones and then applying it here using the Target tab. I'll now add a hot water loop and create a simple hot water heating system to use as a vehicle to highlight important aspects of loops. The hot water loop is used to heat and distribute hot water to heating coils in air handling units or AHUs, and zone terminal units. For demonstration purposes, I won't load predefined templates, but will create the loop manually to enable you to familiarize yourself with the process. To add a loop, I need to be at HVAC system level, where the Add Loop icon becomes visible in the toolbar. You can see from the info panel that there are 3 types of water loop available. I'll cover the other loops in a separate tutorial. Before adding a loop, I'll zoom out to provide space to position the loop next to the zone group. To add a hot water loop, I simply select the option with a left click, move my mouse to an appropriate position in the layout screen, and left click again to confirm the position of the loop. As this will be a very simple system, the position of the loop in relation to the zone group is not too important, but you should always consider the best position for HVAC components in complex systems to keep the schematic diagram as simple as possible. I'll discuss this in more detail when we move on to more complex systems. Once the loop is added, you can see it schematically, and it's also shown in the navigation panel. This means that you can navigate to it in the normal way using the mouse in the layout screen, selecting an object with a single left click, or successively double clicking to access system components. You can, of course, navigate using the navigation tree, which is my preferred method. Whilst in the HVAC system, you're always at building level in the model, as shown by the level indicator here at the top of the layout screen. The navigation panel shows which level you're at within the HVAC system. And here you can see I'm at that hot water loop. The default hot water plant supply subloop includes a single boiler, flow splitter and supply mixer, and a circulating pump. The splitters and mixers in the supply subloop provide the connections to enable you to add boilers, which I'll show you in another tutorial. There is a grey dashed line here between the splitter and mixer on water systems, which represents a flow bypass. This is a protective measure found in real systems which allows water to bypass directly to the return side when there is no demand or flow in the system. There are additional splitter and mixer considerations for more complex systems, which again is covered in another tutorial. The supply subloop also includes a set point manager, which is set up by default to control the hot water flow temperature to a constant 80 degrees C. The position of the arrow on the set point manager symbol shows that it is controlling the flow temperature in the supply subloop shortly after the boiler and supply mixer, just before it enters the demand subloop. The demand subloop is automatically connected to the supply subloop via the grey link lines between the connecting nodes. It currently contains only a splitter and a mixer, but will include relevant zone components such as zone terminal units when they're added to the zone group. The splitter enables supply flow connections to be made up to 50 parallel branches. This enables you to connect different HVAC components such as zone groups and AHU coils in the same way that they would be supplied from pipes branching off from main supply pipes in real systems. The mixer enables water to flow from those HVAC components so it can be returned in a single pipe back to the supply subloop for reheating. Navigating to the demand subloop shows only the splitter and mixer and does not currently show any other connections available. This is because I haven't yet added a HVAC component requiring a hot water supply to my zone group, so the water distribution pipework currently has no supply and return path to and from the condition zones. All connections are made on the demand side of air and water loops. I have the icon available at demand subloop level to enable me to connect to relevant components when they're available. Navigating to the supply subloop zooms into the boiler, pump and setpoint manager. I can navigate to any of the subloop components. I'll now briefly show you the information available to edit for the hot water loop and each of its components. The detail of these edit dialogues is covered in later tutorials. Going to the hot water loop, I can access the edit dialog via the toolbar, the info panel, or using the right mouse button. The General tab includes the loop characteristics, sizing and operational data. So for example, you can define a constant or variable flow control strategy and set your design, exit temperature and system delta T. You'll see this blue auto size input on many of the edit dialogues. If the auto size option is used, that part of the system will be automatically sized and the calculated values used as inputs to the Energy Plus simulation. You can of course enter your own value if you have appropriate data. The Plant Equipment Operation tab allows you to set up different equipment operation schemes for the loop. Going to the boiler, the diagrammatic representation shows the burner and the flue attached to the main heat exchanger with the water flow and return pipes above and below respectively. The edit dialog includes basic information such as the boiler and fuel types and the sizing and efficiency data. The Setpoint Manager defines the control settings for the loop, and the pump dialog contains the sizing, efficiency and controls parameters for the pump. Having reviewed and if necessary edited the data for the hot water loop and its components, I can now add my zone equipment and edit the data for that if required. In this tutorial I'm going to model a very simple hot water convector system just to illustrate the basic process of connecting components. I must navigate to one of the zones to add zone HVAC components like hot water radiators. So I'll just go to the first zone in the navigator list, allowing me to select the zone components. I can select the water convector component by left-clicking on the info panel link, then left-clicking again anywhere in the zone. DesignBuilder will automatically place the component in the correct position on the diagram. This time you can clearly see that it has flow and return pipes extending outside the zone group. to enable you to connect the component to the supply and return flows in the demand subloop. Going back to the zone group, you can see that the components have been added to all zones in the group, as by definition the zone group is for zones served by the same system or type of system. As the water convector component has editable characteristics, they're also added to the navigator list, which I can access and edit. The dialog again contains sizing and operational inputs. Now that I've defined my loop and zone components, I can connect them together. I make loop connections from the demand subloop, which now also shows the convector component connections. Selecting the Connect Components icon and moving my mouse onto the end of one of the lines representing the pipework, you see a green snap point. It doesn't matter which end of the loop I start, but I must connect the supply and flow sides correctly, i.e. return side of the loop to return side of convector. There are arrows available to help us with this, and note that you cannot connect the bypass node here, as this serves a different function. After clicking onto the supply or flow node on the demand subloop, another splitter is added automatically to enable me to connect more components if necessary. I move the mouse in the required direction to enable me to draw horizontal and vertical lines. Drawing guides help me to locate existing endpoints, so I can simply left click to define a change of direction, then left click again on the convector snap point to connect that pipe. I can then do exactly the same to connect the return water flow path. It's advisable to keep the flow and return lines for each component relatively close together, but not overlapping, which will help you to quickly identify your flow paths in larger and more complex schematics. Once all the loops are connected, you should go back to the HVAC system level and check that the schematic is correct. If I've made a mistake, I can go back to the demand subloop, select the object and delete it. If I have a complex system with lots of lines and want to move the zone group or loop to provide a clearer layout, I go to the HVAC system level, select the component and move it in the normal way. The connections and all data associated with the components remain intact. Now that I've checked all my data inputs and connected my loops, I'll run a quick Winter Design Week simulation and select only sub-hourly outputs at 6 time steps per hour, which is the minimum recommended for HVAC simulations. I'll report on all periods to enable me to see setback heating operation and then run the simulation and skip straight to the results. At building level, we can see the total fuel consumption breakdown and the outside air temperature graphs. The fuel consumption associated with the heating system I've just defined is shown in red. This shows the heating system operating in the early hours to maintain the setback temperature in the building, then peaking to reach the set point temperature just prior to occupation. None of the peaks in the graph flatline at the top, which indicates that the system is not significantly undersized. and is able to meet the heating load at design conditions. The load on the heating system reduces through the day as the thermal mass warms up and the heat gains to the space from other sources increase. The load then increases as the ambient temperature drops and the other gains decrease towards the end of the working day. Before reviewing the data at zone level, it's important to note that you access the results by navigating to the required level in the model, not in the zone group, which always shows building level information. When I click on a zone in the HVAC zone group, there is no change to the display, and the navigator panel and indicator here above the analysis screen both show that you're at building level in the model. In the Activity tab, we have a heating set point of 22 degrees C for the occupied zones and 20 degrees C for the reception and circulation areas. Going now to the ground floor east office, we can see that the heating set point is achieved during occupancy, again showing that the system has sufficient capacity. The temperature rises later in the day. Once the heating load is met due to other gains to the space and the absence of mechanical or nap vent cooling. The only significant setback operation is at the weekend and on Monday morning, which would be expected at design conditions. The reception zone tells a different story. This is a fully glazed north-facing zone, so you can see how the air temperature never exceeds the set point, and the load on the heating system is far higher during occupancy. Much more heating is also required outside occupancy, so that the zone temperature does not fall below the setback temperature. At first glance, the ventilation graph here at the bottom looks fairly erratic, but when you look at the scale, it's actually fairly consistent at just over 0.3 air changes per hour. I haven't provided natural or mechanical ventilation in this building, so this graph shows only infiltration, which was set by the best practice constructions template at 0.3 air changes per hour. In this tutorial, I've introduced the HVAC loop concept via the hot water loop and provided some detail on the important factors associated with loops in general. In the next few tutorials, I'll explore HVAC loops and their components in greater detail.